In this video, we look at the double sideband suppressed carrier AM, DSBSC AM signals. Whenever we talk about the spectrum, we talk about the frequency domain. To obtain the frequency domain, we need to take the Fourier transform. The Fourier transform of the modulated signal of U of t, we are going to take Fourier transform of this AC MT cosine 2 pi CT. To obtain the Fourier transform of U of t, we're going to use the modulation property. This is a modulation property we have been reviewed several times. Fourier transform ext cosine 2 pi f naught t. If we take the product in time domain, then if we take Fourier transform, what that equals to? It equals to the spectrum of ext move to f naught, and then the Fourier transform x move to the minus f naught. You sum them up, you take half. So this is a modulation property. We're going to use it. To apply this property, U of t equals to this. So you take the Fourier transform that equals to this cosine signal here. This is cosine signal here. This is FC and this is F naught. This is F naught. This is F naught, right? And then this signal ext here. So ext here in the modulated signal is ACMT. But AC is a constant. You take it out, and half is here. This is a half. Half is here. So AC is here. And then the Fourier transform of EMT, that's EMF. EMT time domain, that's EMF. Okay. And EX of t, Fourier transform of EX. Okay. So therefore, U of F is the message spectrum, the Fourier transform message, move up to FC, and move to the minus FC. You take half because there's AC magnitude in the carrier signal. AC is taken out here. Now you can see the spectrum of the message is moved up to FC, move up to the carrier. So if the carrier is in the gigahertz, then the message being modulated to this gigahertz band now. So this is the purpose of modulation. You can see once we done that, the message is ready to transmit at FC frequency band. Now let's just make hypothesis shape of MF here. So I just made it up. This is a spectrum frequency transform for EMF. Here is 2A. I made it up. Don't ask me why. It doesn't matter why it's a 2A, just for convenience. Okay. MF, you move this to FC. So that's this portion. This portion move up to here. That's FC. And then this spectrum move to minus FC, that's here, that's to the minus FC. The minus FC. And then you take half and multiply by AC. So this is 2A here, you take half, become A. So here, this is A multiplied by AC. Okay. And you sum them up, you sum this two portion up, you got this two, positive frequency and negative frequency. Now we're going to define a couple of terminology here. The frequency components lower than this FC, we call it a lower sideband. And this on the negative frequency band, frequency higher than the negative FC because they're symmetric here. So, and this portion is a lower sideband signal. for the DSBSC signal here. An upper sideband signal defined as a frequency component higher than FC. So this frequency component is higher than the carrier signal. This is a positive frequency. And on the symmetry in the negative frequency, that's this portion. So for positive frequency, the frequency has to be greater than FC. For the negative frequency needs to be smaller than negative FC. If we write in the mathematical form as F, it should be greater than FC. This is a upper sideband, right? And for absolute value of F less than FC, that will be lower sideband. Let's look at this inequality here. Absolute value of F less than FC, what does it mean? This, we learned that in math course, this really means two inequalities. For example, if I have less than 2, what does this mean? X less than 2 greater than minus 2, right? And here that's the same thing. This contains two inequalities. F less than FC if F greater than 0 is 1. When F is positive, and then F greater than minus FC when F less than 0. That contains two inequalities. This inequality here exactly this portion and this portion. So now let's talk about the bandwidth of the signals. So the bandwidth of the message signal here, you can see here, this is a W, this is a minus W. The bandwidth for the message is W minus this DC. So the bandwidth is this much, that's W. Let's look at the bandwidth after modulation. Now we can see here 0 become FC and W become FC plus W. And this point is FC minus W, right? So the same thing here. This spectrum moved to minus FC. And this point here is minus FC minus W. This is a negative frequency, this is a positive frequency. Right? So the bandwidth for the modulated signal is FC plus W, the highest positive frequency that is non-zero, minus the lowest frequency that is non-zero. So FC minus W, what is equals to? Now FC cancel out each other. This is 2W. So you can see the bandwidth. If I want to transmit this signal, I need to allocate 2W bandwidth for this signal. So therefore, the name is double sideband. We have transmit double sideband. We transmit the lower sideband and the upper sideband. So double sideband. And let's see the carrier. We know the carrier signal is at FC here. But in the modulated signal, there is no carrier signal. There's no carrier frequency unless there's a DC component in the message. Suppressed carrier means that we do not transmit the carrier itself unless there is a DC component in the message. For example, if I have a signal like this, if I have EMF 10 hertz, I have 100. And this is minus 10, this is minus 100, right? So if I have EMF like this, suppose this is a 10, no, suppose this is 4, and this is 4, right? The magnitude. Then if I modulate this signal and this spectrum move to FC, then you're going to have this spectrum move to FC here. So this is a FC. And here this is a FC plus 10, and this is FC. And this is FC minus 100, right? And you can see here, there's no carrier frequency here in the modulated signal. I didn't calculate the magnitude, right? Okay, and this is 0, and then you have another portion like this on the negative portion down here, because this is you move this spectrum, this whole spectrum to here, to FC, and then to minus FC here, to minus FC here, and then you take half the magnitude in considering the magnitude of the carrier as well. So there's a magnitude should be calculated. So you can see in this case there's no carrier signal. So therefore the carrier is suppressed for this scheme, for this AM scheme. Therefore the name is double sideband, because you have two sidebands. Suppressed carrier suppressed for this AM signal.